Hi, welcome to Chemistry Visualized. Today we'll be taking a look at the hybridization and molecular shapes of S&P hybrid orbitals. When we are looking at the S&P orbitals, we can predict that simple molecules such as organic molecules to have 90-degree angles, which is reasonable knowing that S orbital is non-directional, sphere-like, and P orbitals are oriented 90 degrees to each other. However, experimental data shows that it is not true. Molecules with 109, 120, or 180 bond angles are common. Valence shell electron repulsion theory, or shortly VSEPR theory, explains that electron pairs repel each other, positioning themselves furthest away from each other. These shapes are impossible to be explained by simple S&P orbitals. Also, S&P orbitals give lowest energy state for an isolated atom in a space, and not so great when it comes to forming bonds. Therefore, it is concluded that S and P orbitals combine to form a hybrid atomic orbital that can separate the electrons further away from each other. Let's look at an example of sp hybridization. The beryllium hydride has electron configuration of 1s2, 2s2, and empty p orbitals. The 2s electron is paired, and one of the electrons must be promoted to the empty 2p orbital before hybridization. Promoting an electron requires excitation energy, but this is more than compensated later by decrease in energy caused by formation of bond. The resulting is the beryllium having s and p orbital. Addition of s orbital to p orbital via constructive or destructive overlap gives us one of the sp hybrid orbitals, and addition of opposite phase gives us the other hybrid orbital. Since sp orbital received one orbital from 2s and one from 2p, it is notated 2sp and makes two orbitals with same energy. The resulting pair of directional sp hybrid orbitals point to the opposite direction to each other while having enhanced electron density to form sigma bonds. The both sp hybrid orbitals can each form a sigma bond with 1s orbitals of the hydrogen. Superimposing these two gives us the beryllium hydride we know. Largest angle possible between two orbitals would be 180 degrees, making sp hybrid a linear shape. Since hybrid orbital got one orbital each from s and p, it has 50% s and 50% p characteristic. This higher s character makes it more electronegative than sp2 or sp3. This is because s orbital is spherical shape, which allows the nucleus to attract evenly in all directions and thus attract closer to the nucleus. Let's look at an example of sp hybridization that already have electrons in p orbital. The acetylene has carbon which has 1s2, 2s2, 2p2 electron configuration. Similar to beryllium hydride, an electron from 2s2 orbital is moved to the empty p orbital. Then, the 2s orbital and one of the three 2p orbitals is combined to make sp hybrid orbitals. Let's bring in another carbon to make complete molecule. The two carbon atoms with enhanced electron density is in close approximation and thus forms sigma bond. On the opposite sides, the hydrogens form sigma bonds too. The two unused 2p orbitals that remain unhybridized forms two pi bonds. Pi bonds have highest electron density at the center of the two lobes, above and below the sigma bond. Since pi bond is overlapping sideways, it is weaker than the sigma bonds. Moving on to next, we are looking at an sp2 hybridization. The boron hydride has electron configuration of 1s2, 2s2, 2p1. An electron from 2s2 can be moved to one of the empty p orbitals. One 2s orbital and two 2p orbitals are used to make three hybrid orbitals. Since 1s and 2p orbitals are used, it will be notated sp2 orbital. The largest bond angle between three equivalent orbital is 120 degrees. Three sp hybrid orbitals of boron will form three sigma bonds with three hydrogens to make boron hydride. Since the hybrid orbital got one orbital from s and two from p, it would have 33% S characteristic and 66.7% P characteristic. This hybrid orbital would have bond angle close to 120 degrees. How about ethylene? It is also a sp2 hybrid, but it has electron configuration of 1s2, 2s2, 2p2 in the beginning. Similar to the boron hydride, one electron from 2s2 is moved to the empty p orbital. One 2s orbital and two 2p orbitals are used to make 3 hybrid orbitals while leaving one of the p orbitals unhybridized. 3 sp2 hybrid orbitals of carbon will form 3 sigma bonds with another carbon and 2 hydrogens. The unused 2p orbitals that remain unhybridized forms pi bond. Last thing we're going to cover is the sp3. Methane is an example. We got pretty familiar with the carbon and how their electron will be moved to p orbital. The s orbital and all 3 p orbitals will combine to make 4 sp3 hybrid orbitals. The 4 sp3 hybrid orbitals will form 4 sigma bonds with 4 hydrogens. Since this hybrid orbital got 1 orbital from s and 3 from p, it would have 25% s characteristic and 75% p characteristic. sp3 would have least electronegativity due to highest p characteristic compared to sp and sp2. Largest angle possible with 4 orbits would be close to 109.5 degree, making a tetrahedral molecule. Today we viewed that hybridization of s and p orbitals. Hope this was helpful in visualizing. Also consider subscribing if you love the content. More visuals coming soon.